Work that we've done recently, just in the last year, is finding ways to tweak the cells and the tissues of mice, at least, to reset the clock. We've been working for 10 years, as I said, accelerating the clock. We can drive that hand of the clock forwards now. We cut the DNA of the animal, let it heal, and in doing so, we distract those proteins from where they come from. So we're disturbing this survival circuit so much that we disrupt the spooling of the DNA. And what we got was an old mouse, by every account, based on histology, which is looking at the tissues, based on their physiology. They got gray, they got arthritis, they got heart disease even. And when we look at the molecular clock, that methylation clock, they were 50% older compared to
they had more like clumps everywhere.
Those methyl groups were added
to the DNA.
Right. So we had given them heart disease and Alzheimer's or dementia. We'd given them all these diseases, but by measuring the clock, what we had actually done is give them aging. That was the first step. That took 10 years. The last year, we've been asking, how do you get the hands to go backwards? That's a lot harder. But we were fortunate. The 2012 Nobel Prize was won for the ability to reverse that clock in cells. It's called prize awarded to Shinya Yamanaka, a Japanese fellow, very smart guy, and he found at least 4 genes that when you put into, say, skin cells of an adult, if you gave me your skin cells, I could go back to the lab and basically clone you. I could take your cells, make a stem cell pool, and I could grow you into a new little liver or a new little kidney. That's all easy, not easy, but it's doable.
Wow.
It's doable. What that tells us is that those 4 Yamanaka genes can reset age. If I can take someone who's in, like you, who's in their early 40s and make a new you, as we've done now for many species, dogs, cats, sheep, monkeys, those animals, we can reset the clock 100%, and those animals actually live a normal lifespan. That tells us that the instructions to be young are still in the cell somewhere. As though there's a backup hard drive that tells the epigenome, those spools, how to go back to be young again and get those methyl groups back to being young again. Not up here, but back there. But don't strip them off too far to be a stem cell, or I'll basically turn you into the world's giant tumor.